Welcome to this module on working with self-managed nodes. In this module, we'll dive into the world of self-managed nodes, where you get complete control over the worker nodes within your OKE environment. A self-managed node is a worker node hosted within the compute instance or instance pools that you have created within the OCI compute service, providing you with flexibility and customization options beyond what managed nodes offer. So let's begin. Hello and welcome to this lesson on OKE self-managed nodes, overview and prerequisite. I am Mahindra Mehra and I am a senior OCI instructor at Oracle University. So let's get started. In Container Engine for Kubernetes, a self-managed node is essentially a worker node that you personally create and host on a compute instance or instance pool within the compute service. Unlike managed nodes or virtual nodes, self-managed nodes are not grouped into node pools by default. They are often referred to as bring your own nodes, also abbreviated as BYON. If you wish to streamline administration and manage multiple self-managed nodes collectively, you can utilize the compute service to create a compute instance pool for hosting these nodes. This allows for greater flexibility and customization in your Kubernetes environment. Now, let's delve into the usage scenarios for OKE self-managed nodes. These nodes offer a range of advantages for specific use cases. Firstly, for specialized workloads, leveraging the compute service allows you to configure compute instances with shapes and image combination that may not be available for managed nodes or virtual nodes. This includes options like GPU shapes for hardware accelerated workloads or high frequency processor cores for demanding high performance computing tasks. Secondly, if you require complete control over your compute instance configuration, self-managed nodes are the ideal choice. This gives you the flexibility to tailor each node to your specific requirements. Additionally, self-managed nodes are particularly well suited for Oracle Cloud Infrastructure cluster networks. These nodes provide high bandwidth, low latency RDMA connectivity, making them a preferred option for certain networking setups. Lastly, the use of compute instance pools with self-managed nodes enables the creation of infrastructure for handling complex distributed computing tasks. This can greatly enhance the efficiency of your Kubernetes environment. Consider these points carefully to determine the optimal use of OKE self-managed nodes in your deployments. Let's talk about the prerequisites you need to consider before creating a self-managed node and integrating it into a cluster. There are two crucial aspects to address. Firstly, you need to confirm that the cluster to which you plan to add a self-managed node is configured appropriately. We'll delve into the specific cluster requirements shortly. And secondly, it's essential to choose the right image for the compute instance hosting the self-managed node. We'll explore the image requirements in the upcoming slides. Stick with me as we break down these prerequisites for seamless self-managed node creation and integration into your cluster. Now, let's deep dive into the specific cluster requirement for adding self-managed nodes. To successfully integrate a self-managed node into your cluster, you must ensure that the cluster is an enhanced cluster. This is a crucial prerequisite for the addition of self-managed nodes. Make a note, the Flannel CNI plugin for pod networking should be utilized, not the VCN native pod networking CNI plugin. This ensures optimal pod networking for your self-managed nodes. The control plane nodes of the cluster must be running Kubernetes version 1.25 or later. This is essential for compatibility and optimal performance. Lastly, maintain compatibility between the Kubernetes version on control plane nodes and worker nodes, with a maximum allowable difference of 2 minor versions. This ensures a smooth and stable operation of your Kubernetes environment. Keep these cluster requirements in mind as you prepare to add self-managed nodes to your OKE cluster. Moving on to the image requirements for self-managed node creation, pay close attention to these key points. Choose either Oracle Linux 7 or Oracle Linux 8 image for your self-managed nodes. Ensure that the selected image has a release date of March 28, 2023 or later. Obtain the image OCID, also known as Oracle Cloud Identifier, from the respective sources. OKE Worker Node Oracle Linux 7.x images or OKE Worker Node Oracle Linux 8.x images, and this information is crucial for specifying the correct image. When specifying an image, be mindful of the Kubernetes version it contains. It's your responsibility to select an image with a Kubernetes version that aligns with the Kubernetes version's Q support policy, as outlined in the Kubernetes documentation. Keep in mind that the container engine for Kubernetes does not automatically check the compatibility, so it's up to you to ensure harmony between the Kubernetes version on the self-managed node and the cluster's control plane nodes. These considerations will help you make informed choices when configuring images for your self-managed nodes. To wrap up, in this lesson we covered container engine for Kubernetes, self-managed nodes, emphasizing their flexibility for specialized workloads and custom configurations. Prerequisites included enhanced clusters, specific CNI plugins, and image requirements. OKE's self-managed nodes offer versatile and controlled Kubernetes deployments. I hope you found this lesson insightful. See you in the next one. Thank you for watching. Hello and welcome to this lesson on creating self-managed nodes in Container Engine for Kubernetes. In today's session, we will delve into the process of establishing self-managed nodes, and it will be a dynamic blend of theory and practical demonstration. So let's get started. Alright, let's jump into the good stuff, creating a self-managed node for your OKE cluster. And here's the game plan. First step is to create a dynamic group. We must generate a dynamic group inclusive of a rule that encompasses the compute instance and the policy statement, allowing group members to join the cluster. Next step is to create a cloud init script that incorporates the Kubernetes API private endpoint and a base64 encoded certificate authority certificate specific to the cluster. Lastly, instantiate a new compute instance utilizing an OKE image as the base and supply the created cloud init script to it. In the next few slides, we will take a closer look at each of these steps, and of course, I'll cover the same using demonstration. Let's roll. Let's dive into the first step of creating our self-managed node, that is setting up the dynamic group and its policy. Firstly, we have to define a dynamic group, and we need to add a rule that includes the compute instances in the compartment. Here's the format, and just replace compartment OCID placeholder with the OCID of the compartment where your cluster resides. Next thing is to craft a policy that allows compute instances in the dynamic group to join your existing Kubernetes cluster. And this is the policy that you must specify to allow dynamic group to join cluster in compartment and the name of the compartment. Remember, this is the compartment name where you are hosting your cluster. And if you find this policy statement too broad, you can fine tune it by explicitly specifying the cluster that you want to target. As given in this policy, using a where clause, you can specify or fine tune to which cluster you want to target by simply providing the cluster OCID in the policy. I'll now transition to the OCI console and show you that I have created the dynamic group and the required dynamic group policy. Well, I've logged in into my OCI console and let me take you to the dynamic groups. I'll be selecting dynamic groups under the identity domain section. And this is the dynamic group that I created, where I have this rule which specifies all instances in my compartment. And this is the OCID of my compartment CTD OKE. Now let me show you the dynamic group policy. Let's head back to the identity service page. I'll click on policies. And the dynamic group policy has been written in the parent compartment of my CTD OKE compartment, which is Mahindra. Let me select the compartment. And this is the dynamic group policy for the self-managed nodes. The policy says allow dynamic group self-managed nodes OKE, which was the name of my dynamic group, to join the cluster in compartment CTD OKE. Let's head back to our slide deck and continue with the next steps. Let's get hands-on with creating a cloud init script for our self-managed node. And here are the steps. Firstly, we'll have to obtain the Kubernetes API private endpoint of the enhanced cluster that we'll be using to connect our self-managed node. To obtain the Kubernetes API private endpoint IP address, you must select your cluster, and under the cluster details page, you have to copy the IP mentioned under the Kubernetes API private endpoint label. Remember, you just have to copy the IP address and not the port number. Let's see what is the Kubernetes API private endpoint for the cluster which we will be using for our demo. Let me navigate to the Kubernetes cluster service. The compartment in which our clusters are running is CTD OKE. And this is the cluster that I'll be using for this demonstration. Let me select the cluster. And under the cluster details tab, I simply need to copy the IP address for my Kubernetes API private endpoint, which in my case is 10.0.0.2. Let me make a note of it. Alternatively, you can obtain Kubernetes API private endpoint using the OCI CLI command. You must run the following OCI CLI command to get the Kubernetes API endpoint private IP address. Just replace the cluster OCID with your cluster OCID and the region identifier with your respective region identifier. Let's run this command in Cloud Shell terminal and obtain the Kubernetes API private endpoint of our enhanced cluster. I'll spin up the Cloud Shell machine. Firstly, I need to copy the OCID of my cluster. Let me copy the OCID of my cluster from the cluster details page. Now let me edit the command. I'll simply replace the OCID of my cluster. The region in which I'm working is US West Phoenix and the region identifier is US-Phoenix-1. Now I'll run this command in the Cloud Shell terminal. Well, as you can notice, we have retrieved the IP address of our Kubernetes API private endpoint using the CLI. Now we must obtain the cluster's base64 encoded CA certificate, and for which we must execute the following OCI CLI command to extract the base64 encoded CA certificate. Remember to replace the cluster OCID and region identifier placeholders with your enhanced cluster OCID and the respective region identifier. Let's head back to the OCI console and obtain the cluster's base64 encoded CA certificate. Make a note that the base64 encoded CA certificate is shown in the Cloud Shell window as a long alphanumeric string that starts with character LS0T. Well, this is the command, and I've updated the cluster OCID in the command as well as the region identifier. Now I'll run this command in the Cloud Shell terminal. And it has returned me the base64 encoded CA certificate. I'll copy the entire string. Now in a text editor, we will create the cloud init script as given on the screen. In the script, we must replace these placeholders like the cluster endpoint with the IP address of our Kubernetes API private endpoint and the string that we copied for the base64 encoded certificate. And we must save this text file for use when we create the self-managed node. Well, I have my script ready where I have provided the IP address of my Kubernetes API private endpoint as well as the base64 encoded CA certificate of my cluster. Since this video is getting a bit longer, I'll pause here and we will continue in the next part. I hope you're liking the video so far. See you in the next video. Welcome back. Let's begin from where we left off in the last session. Finally, you must create a compute service to create the compute instance on which you will be running the self-managed node. And having created the self-managed node, you will then add it to an existing OKE cluster of enhanced category. Let's continue our demo by creating the new compute instance for our self-managed node, and here are the steps. Step 1 is to create compute instance. We will kick things off by creating a brand new compute instance to play host to our self-managed node. We must ensure that there are appropriate policies in place to allow this new compute instance to seamlessly join the enhanced cluster. Let's transition back to OCI console and start with step 1. To create compute instance, I'll navigate to the compute service and click on instances. I'll make sure that I'm in the right compartment. The compartment where I'm creating this compute instance for the self-managed node is the ctdoc compartment, and this is the compartment where our Kubernetes cluster is running. I'll click on create instance to start creating the instance. Give it a suitable name. Under the placement, I'll go with the default selection. I'll scroll down to the image and shape section. In step 2, we must choose the right image. And in the image and shape section, we must click on change image and opt for image OCID and enter the desired Oracle Linux 7 or Oracle Linux 8 image OCID. Let's head back to our OCI console and perform this step. Here, we must click on change image and select my images and opt for image OCID. And here we must provide the image OCID. Let's navigate to the official documentation, and in the image requirements, it's clearly mentioned the image you specify for a self-managed node must be one of the OKE Oracle Linux 7 or Oracle Linux 8 images. To obtain the image OCID, we can click on these hyperlinks. Let me go ahead with Oracle Linux 7 image. Now from the list of images that are available, I'll be selecting the first image on the list, And this one is running the Kubernetes version 1.27.2, which is similar to the one that our cluster is running on. To obtain the OSID, I'll click on the link. You scroll down, you get to see the OSIDs for respective regions. I'll be copying the OSID for the region I'm working in. The region I'm working in is US West Phoenix, which is why I'll be copying this OSID over here. Let me navigate back to our compute instance page and provide the image OSID. Well, it has fetched the image details, and now I'll select image. Leave the shape as default, whichever is compatible with our image. Under the primary VNIC information, I'll leave it as blank. And under the primary network, I'll select the virtual cloud network on which our cluster is running. And Acme Dev VCN is the VCN where our cluster is running, which we'll be using to attach our self-managed node to. And under the subnet option, we must select the worker node subnet. In our case, the worker node subnet is a private regional subnet. I'll select the worker nodes regional option. You can even add an SSH key so that you can later on SSH into your self-managed node, for which we must provide a public key over here. Let me choose the paste public key option and paste the public key of the SSH key pair that I have in my Cloud Shell machine. Now in step 3, it says that we must select the advanced options. And on the management tab, we must select the paste cloud init script option and paste the cloud init script with the Kubernetes API endpoint and the CS certificate which we created. I'll be selecting show advanced options. And under the management tab, I'll be selecting the paste cloud init script option. And I'll be pasting the cloud init script that I created. This is the cloud init script that I created where I have the Kubernetes API private endpoint and the space64 encoded CS certificate. Time to seal the deal. We will hit that create button to bring our compute instance to life. Upon creation, it seamlessly will join the ranks as a self-managed node in the OKE cluster. I'll click on the create button here. And the compute instance is in the provisioning state. As the compute instance materializes, it becomes a fully fledged self-managed node in the cluster, armed with Kubernetes API endpoint that we specified. In the meanwhile, let me bring back the Cloud Shell terminal. I'll clear the screen. And I'll show you the number of nodes that currently exist in our Kubernetes cluster. Well, the cluster to which we'll be attaching our self-managed node currently is running with a single pool having 3 nodes in it. Once the compute instance is provisioned, we will be able to see a 4th entry for our compute instance as a self-managed node in our cluster. Let's wrap things up by ensuring our self-managed node is seamlessly integrated into our Kubernetes cluster, and here's how you can verify it. By running the kubectl get nodes command and see if there is an entry for our self-managed node and the status must be ready. Well, the compute instance is up and running. Let's go back to the Cloud Shell terminal and let's run the kubectl get nodes command. As you can notice, we have an entry for our self-managed node. Currently, the status says not ready. It will take some time before the status changes to ready. But in the meantime, let me cross-check the IP address. This is the private IP address of our compute instance. Let's check if this IP matches to the compute instance private IP address that we just created. This one is ending with 209. And our private IPv4 address for the compute instance also ends with 209, which means they both match. Well, as you can notice, our self-managed node with the IP address 10.0.1.209 is in ready state. You can also confirm that the labels have been added to the node and set as expected. Let's head back to our OCI console and run this command to see it in action. Well, this is the command kubectl get node and the node IP address of our self-managed node. Get the output in JSON format and only display the metadata labels. From the labels, it is clear that the node is the self-managed node, which is running on a compute instance and connected to our cluster, having instance type VM standard A1 flex. As we wrap up, let's highlight some key points crucial to managing self-managed nodes effectively. If you delete a cluster with self-managed nodes, remember that the compute instances hosting these nodes won't terminate automatically. It's your responsibility to manage the termination of these instances. Be aware that the containers currently running on the nodes might persist after cluster deletion, as long as they are not dependent on the Kubernetes control plane. Optimize your approach by using compute service to create a compute instance pool. This allows you to effectively host one or more self-managed nodes, providing a streamlined and scalable solution. Use the instance configuration wisely. You must define an instance configuration that includes essential details like the cluster's Kubernetes API private endpoint and base64 encoded CA certificate in a cloud init script. And this script can be utilized to create individual instances or instances with an instance pool, each capable of hosting a self-managed node. One important point to note is when you upgrade the version of Kubernetes running on a self-managed node, you will have to replace the existing self-managed node with a new self-managed node. To wrap up, in this lesson, we explored the dynamic realm of OKE self-managed nodes, unlocking insights into usage scenarios, creation intricacies, and crucial considerations. Thank you for joining us, and I'll see you in the next video. Welcome to this module on managing your Kubernetes deployments. In this power-packed module, we'll explore a variety of options to effectively manage your Kubernetes deployments. From deploying multi-tier applications using kubectl to pulling images from container registries during deployment, we will cover all the essential steps required to streamline your deployment processes. Additionally, we'll dive into topics like understanding supported labels during cluster creation and management, defining Kubernetes service of type load balancer, managing ingress controllers, and working with OCI native ingress controller. We will also cover advanced deployment techniques, including deploying Oracle Cloud Infrastructure Service Operator for Kubernetes, also known as OSOK, an open source Kubernetes add-on that allows you to manage OCI resources. And don't forget, we'll also cover deploying applications for special use cases on both ARM-based and GPU-based nodes, ensuring you're well equipped to handle diverse deployment scenarios. And like always, we have demos to bring concepts to life and ensure thorough understanding. Let's begin. Hello and welcome to this demo on deploying a multi-tier application on a OKE cluster using kubectl. In this tutorial, we'll walk through building a multi-tier web application on Container Engine for Kubernetes, also known as OKE, and our application is a guest book allowing users to enter text and view the last few entries. We will be creating a Redis leader instance and a Redis leader service. The guestbook application will require it to communicate to the Redis to write its data. The Redis leader is a single pod. We will then set up Redis follower pods and Redis follower service. The guestbook application will need this service to communicate with the Redis followers to read data. Once we have the Redis storage of our guestbook up and running, we will start the guestbook web server. Basically, the guestbook app uses a PHP frontend and it is configured to communicate with either Redis follower or Redis leader service depending on whether the request is a read or a write. The Redis leader service and the Redis follower service is only accessible within the Kubernetes cluster because the default type for a service is cluster IP. But since we want our guestbook web application to be accessible externally, we will create the front-end service using a load balancer service type. Let's transition to OCI console and start with deploying this guestbook application, which is a multi-tier application on our Container Engine for Kubernetes. Well, I've logged into my OCI console, and before diving into the application, we must ensure that we have an OKE cluster, and in the interest of time, I'll be reusing an existing cluster. I'll go to the Kubernetes cluster service. I'll click on developer services, and within container and artifacts, I'll click on Kubernetes clusters. For this demo, I'll be using the OKE public demo 1 cluster, and I'll be using the Cloud Shell terminal to set up my multi-tier application on this cluster. I'll open up the Cloud Shell terminal by clicking on Cloud Shell. I'll also open the code editor to have a better view of the manifest that we'll be using throughout this demonstration. Well, both the Cloud Shell terminal and the code editor is now available. Like I mentioned, I'll be using an existing cluster that is OKE public demo 1 to run this demonstration. I'll reconfirm if I have the access to this cluster using the kubectl command line utility. I'll run the kubectl get nodes command to confirm that. Well, these are the list of nodes it has returned, and just to confirm if I'm connected to the same cluster, I'll quickly go and check the node pools and the worker node IPs. Well, the worker node IPs end with 149, 26 and 150 for this cluster over here. And if I check in my console output, it's 149, 150 and 26. Which means I'm connected to the right cluster where I'm trying to set up this multi-tier application. I'll clear the screen now. I'll open up the folder in which I have all the manifests stored. Let's start by setting up the Redis leader, that is the backbone of our guestbook application, and we'll be using the redis-leader-deployment manifest file to deploy a single replica Redis leader pod. I'll open up this manifest file. This is the manifest for the Redis leader deployment. As you can notice, the kind is deployment, and in the metadata section, we have the name given to it as Redis-leader and the supporting labels for our deployment, where it says app Redis, role is leader, and tier is backend. Under the spec section for the deployment, we've specified the replica set, which is one instance for this pod. And under selector, we are defining the match labels where it has to match the pod whose label is app Redis. And in the pod template, as you can notice below, we have defined the labels, and in the spec section, we have defined the name for our container and the image that it must pull for this Redis leader. And under resources, there's a request property for CPU and memory. Also, the port at which the Redis leader would listen is 6379. Now I'll use the kubectl command to deploy the Redis leader deployment manifest file. Let me switch to this examples directory. and I'll run the kubectl command to apply this manifest file. Command is kubectl apply -f and the name of the file, which is redis leader deployment.yaml. Alright, the output says deployment Redis leader created. Let's quickly check whether the Redis leader pod is created or not. I'll be using the command kubectl get pods, and as the output says, the Redis leader pod is up and running. Now to enable communication with the Redis leader pod, we'll create the Redis leader service. This service acts as the gateway for data writes, allowing the guestbook application to interact with the Redis leader pod. I'll head back to the OCI console and I'll show you the manifest for our Redis leader service. Let me click on it. And this is the manifest for our Redis leader service. As you can notice, the kind says service. Here is the metadata for this service, where we are using the name as Redis leader and the labels is similar to the one we had in the deployment. And under the spec section, we are defining ports. The target port on which this service would connect to the deployment pod is 6379. And again, we are using selector label to define the object to which this service should bind. And as you can notice, the selector says these are the labels that it should bind to, which is similar to the ones we had defined in our pod template. I'll minimize this window and I'll run the kubectl command to create this service. Command is kubectl apply -f and the service name is Redis leader service.yaml. Well, the output says service Redis leader service created, and it will create a service of type cluster IP. Let's check whether the service is created or not. Let me use the command kubectl get svc to check the service detail. And yes, the Redis leader service of type cluster IP has been created, which is using the port 6379 to listen on. Now let's enhance the availability by adding Redis followers. We will be using the Redis follower deployment manifest file to deploy 2 follower replicas. And basically these followers will improve data read performance and provide more fault tolerance to our application. First, I'll show you the manifest for our Redis follower deployment. I've opened up the file in code editor, and this is the manifest for our Redis follower deployment. As you can see, the kind specifies deployment. This is the metadata where we have specified the name for our deployment and the labels. Under the spec section, we've defined the replica set, that is 2 replicas for the pod in this deployment must be created. And under the template section, we've defined the labels for our pods, which is app Redis, role is follower, and tier is backend. And under the spec section, we've defined the properties for containers, that is the name of the container, the image from where it should be pulled, the resources like the CPU and memory request, and the ports where the container must listen, that is 6379. Let me minimize this. And let's apply the Redis follower manifest file. I'll hit enter over here. And it says deployment.app/Redis follower created. Let's check whether the pod for Redis follower, basically 2 instances of Redis follower pods are created. Alright, as we can notice, the 2 instances of our Redis follower pods are up and running. Now the next step is to ensure that the Redis followers are discoverable by setting up the Redis follower service. This service facilitates data reads by routing traffic to the Redis follower pods, enhancing overall application resilience. I'll head back to the OCI console and let me bring up the Redis follower service manifest. This is the manifest for our Redis follower service. The kind specifies service, and we have the metadata for this service, which says Redis follower and the labels defined. Under the spec section, we have defined port, where the port this service should serve on is 6379. The selector field basically tells the service which pod it should associate with, and send the traffic to, which is why our selector here matches the labels that we have defined in the Redis follower deployment. I'll minimize this window and apply the service manifest file for Redis follower. I'll first clear the screen. Use the kubectl apply command. And let's give the name of the file, which is Redis follower service.yaml. I'll hit enter. And there you go. The service for Redis follower is created. Let's check whether the service is active using the kubectl command. And yes, we have the Redis follower service of type cluster IP that is available and listening on port 6379. I hope you are liking the video so far. See you in the next one. Thank you for watching. Welcome back. Let's resume from where we left off in our last video. Now with Redis in place, let's deploy the guestbook web servers. We have a deployment manifest file which configures the deployment for the PHP-based guestbook application. The guestbook web server communicates with both the Redis leader and the Redis follower, ensuring a seamless user experience. Now I'll bring up the manifest for our front-end deployment, which is frontend-deployment.yaml file. The API version is apps v1. The kind is deployment. Under metadata section, we have defined information like the name to our deployment. Under the spec section, we have defined the replica sets. Basically, 3 replicas of the pods running in this deployment must be available at any point in time. And the label selector is used to identify the pods that we must match to, which is app guestbook and tier frontend. Then we have defined the template for our guestbook application, where under the metadata section we have defined the labels, which is app guestbook and tier frontend. Under the spec section we have defined the containers information like the name for our guestbook PHP application, the location of the image where it should be pulled from. The image pull policy says that always pull a fresh image. The manifest file also specifies environment variable get_host_from, and the value is set to DNS. Basically, when you provide the configuration to guestbook web frontend application, the frontend application uses the host names like Redis follower and Redis leader to perform a DNS lookup. The DNS lookup finds the IP address of the respective services that we have created in our previous step, and this concept is called as DNS service discovery. And the port on which our web application is exposed is port 80. Now I'll minimize this window and apply the manifest for our front-end web application. Alright, the deployment has been created. Let's check the deployment status. The rollout has been completed successfully. Now let's check the pods. There you go. We have the 3 pods running our web application up and running. Let's quickly check the services that we created in our previous step. The Redis follower and Redis leader services that we created in the previous step are only accessible within the OKE cluster because the default type for the service that we have used is cluster IP. And cluster IP provides a single IP address for the set of pods that the service is pointing to, and this IP is accessible only within the OKE cluster. However, we will be needing the guestbook web frontend service to be externally visible. That is, we want our client to be able to request the service from outside the OKE cluster. And to accomplish this, we will be using the service type of load balancer in our service manifest file for the front end service. I'll maximize this window and I'll bring up the front end service manifest. Well, this is the manifest for our front-end service. As you can notice, the kind says service, and the metadata is defining the name for our service. Under the labels, in the metadata section, we've defined the key values like the app, guestbook, and tier frontend. And under the spec section, we've defined the type as load balancer. The port on which the load balancer would listen is port 80, and we are using the label selector to connect to the pod which is running our front-end web application, whose labels are app, guestbook, and tier frontend. These labels match the labels we have defined for our containers, or you can say pod, in our deployment file. As you can notice, the labels are app, guestbook, and tier is frontend. Matches the label selector under the specification defined for our front-end service. I'll clear the screen first, and now I'll apply the front-end service manifest using the kubectl command. The output says service front-end created, and let's check whether we have a load balancer IP assigned to our front-end service. It does take some time before the load balancer is created and the IP address is assigned. Let's check. Well, the entry is available for our front-end service of type load balancer, but the external IP is yet to be assigned. We'll wait for some while before the external IP is visible here. Let me retry getting the service details. Well, this time we have the external IP available. Now to access our guestbook web application, I'll copy this IP and paste it on a new tab. And there you go, our guestbook application is accessible. Now let's experiment with this guestbook by entering a message and clicking on submit. And as you can notice, the guestbook application is up and running, and we are able to send message to the Redis storage and also retrieve it on the screen. Let me add another message. And let's hit submit. And as you can notice, the second message that I submitted is also visible on the screen. Now envision a scenario where this guestbook attracts significant attention, and to handle this influx, we can easily scale up the web frontend. Let's scale up this web frontend application. I'll be using the command kubectl scale deployment and the name of the deployment, that is frontend, and scale the replicas to 5. Currently it is running with 3 replicas. I'm scaling it up to 5. I'll hit enter over here, and it says the deployment frontend has been scaled. Now let's check the number of pods. And if you notice, the number of pods for front-end deployment have increased from 3 to 5. Well, that's it from this demo. And as we conclude this demonstration where we saw how to deploy a multi-tier web application on Container Engine for Kubernetes, showcasing the seamless interaction between Redis and Guestbook PHP front-end application. If you are looking to delve deeper into Kubernetes or shadow this demo, I recommend exploring the official Kubernetes documentation available on the Kubernetes official site. Here you will find the detailed step-by-step tutorial for deploying the application that we just deployed on OKE cluster. You can find this tutorial in the tutorial section on the kubernetes.io official documentation site. And to reach to this tutorial, you must click on stateless applications and click on the example link given here. I hope you found this demo interesting. Stay tuned for more such videos. Thank you for watching, and I'll see you in the next video. Hello and welcome to this lesson on pulling images from registry during deployment. I am Mahendra Mehra, Senior OCI Instructor at Oracle University. Let's get started. In this lesson, we'll dive into the process of pulling images from Oracle Cloud Infrastructure Registry during deployment in a Kubernetes cluster. During the deployment of an application to a Kubernetes cluster, you'll typically want one or more images to be pulled from a container registry. In the application's manifest file, you specify the images to pull, the registry to pull them from, and the credentials to use when pulling the images. The manifest file is commonly also referred to as pod spec or as the deployment.yaml file, although other names are allowed. If you want your application to pull images residing in Oracle Cloud Infrastructure Registry, you need to perform two essential steps. First, use kubectl to create a Docker registry secret containing OCI credentials. Second, specify the image details including the repository location and the Docker registry secret in the application's manifest file. To create a Docker registry secret, use the kubectl create secret command. Remember to set up the cluster's kubeconfig file and replace the placeholders with the appropriate values. Make a note that certain special characters need to be surrounded by single quotes. Placeholder like secret name is the name of your choice. As you can see in the example, we've given it a name OCIR secret. Region key should be replaced with the key for the Oracle Cloud Infrastructure Registry region you are using. In this case, as you can see, it's PHX. OCIR.io is the Oracle Cloud Infrastructure Registry name. So what completes the Docker server name is region key.ocir.io, as in this case it is phx.ocir.io. PHX here represents Phoenix region. Next is the tenancy namespace. It is the auto-generated object storage namespace for your tenancy. You can find this information in your tenancy information page under your user profile settings. Make a note that the object storage namespace can be a random string, and for some older tenancies, the namespace string might be the same as the tenancy name in all lowercase letters. Next is OCI username. It is the username to use when pulling the image. Next is OCI auth token. And the OCI auth token is the auth token of the user that you have specified in the username field, that is OCI-username. Remember, special characters like auth token must be surrounded by single quotes. And lastly, you specify the email address for your Docker email as given in the example. And let me reiterate that some strings containing special characters such as parentheses must be surrounded by single quotes. Basically, it's the auth token that may have such special characters. Moving on, to specify the image to pull from Oracle Cloud Infrastructure Registry along with Docker secrets to use during the deployment of an application to OKE cluster, we must open the application's manifest file in a text editor, add a container section that specifies the name and the location of the container you want to pull from the OCIR repository, along with other deployment details like image pull policy and ports definition. You must then add an image pull secrets section to the manifest file that specifies the name of Docker secret you created to access the Oracle Cloud Infrastructure Registry. Recollect from the previous slide, OCIR secret is the name of the secret we created using the command we discussed on the previous slide. In summary, we have covered the steps to pull images from a container registry using deployment, especially when dealing with Oracle Cloud Infrastructure Registry. Editing the application manifest is a crucial step in this process. I hope you found this video informative, and I'll see you in the next video where we have a demo planned around this concept. Thank you for watching. Hello and welcome to this demo on pulling images from registry during deployment. I am Mahendra Mehra, your senior OCI instructor at Oracle University. Let's get started. In the previous demo, we successfully deployed a multi-tier guestbook application utilizing container images sourced from third-party repositories with public access. Now, in this demonstration, we are set to introduce a significant change, and I'll be modifying the front-end deployment manifest to fetch the guestbook application from Oracle Cloud Infrastructure Registry. Now, before we proceed with this adjustment, I'll first delete the existing deployment resources for our front-end application. I'll first navigate to the guestbook directory where we have the manifest files included. Here I'll use the kubectl delete command to delete the front-end deployment. I'll hit enter. And it says the deployment front-end has been deleted. Let's confirm that using the kubectl get pods command. And as you can notice from the output, we don't have the front-end pods running on the Kubernetes cluster. Now, if I go back to our guestbook application and I hit refresh, as you can see, the page is no longer accessible. Now let's navigate to the OCIR service. I'll click on the navigation menu and click on Developer Services, under which I'll click on Container Registry. Within my CTD OKE compartment, I have already created a repository and hosted my guestbook application within this repository. The repository name is Mahendra/guestbook, and this is the guestbook application front-end container image. I have hosted the guestbook PHP web applications container image in a private repository titled Mahendra/guestbook. And this is the image, which is version 1 for our guestbook application. I'll restore the Cloud Shell terminal. And now I'll go to my front-end deployment manifest. And here I'll replace the container image location with the location of the image in my Oracle Cloud Infrastructure Registry repository. In order to find the container image location, you can simply click on the copy pull command and paste the command in a word editor. And as you can notice, this is the location from where we can pull the guestbook web application hosted on our Oracle Cloud Infrastructure Registry repository. I'll copy this location. Let me minimize the word editor and let's head back to our code editor and replace the existing container image location with the one that we just copied. I'll save the file now. Now on my Cloud Shell terminal, I'll rerun the deployment manifest using the kubectl command. I'll hit enter. It says the deployment front-end created, but now let's check whether the pods are running or not. I'll use the command kubectl get pods. And the pods are not ready as they have errored out saying error image pull. Let's debug further and see why are these pods not running. Let's use the kubectl describe pod command. Let's use one of the pod names. I'll hit enter here. And as you can notice from the events, it says it was trying to pull the image from the container image location we specified in the deployment manifest, but it failed to pull the image. And the error message says anonymous users are only allowed read access on public repos, which means the deployment failed at pulling the image from the private repository. And which is why we must first create a Docker secret and supply it as an image pull secret argument in our deployment manifest file. Now let's go ahead and create the Docker secret. Well, this is the command to create the Docker pull secret. The command is kubectl create secret docker-registry and the name of the secret, which is OCIR secret. We are specifying the Docker server location, which is phx.ocir.io, as I have created my Oracle Cloud Infrastructure Registry repository in the US West Phoenix region, which is why I've used the phx region key. The docker-username is the tenancy namespace / separated by the username using which you're operating the Oracle Cloud account. And then we have the docker-password where we are specifying the auth token that we have generated for this user running the cloud account. And finally, we are specifying the Docker email. Now let me show you where to fetch the information like your tenancy namespace. For your tenancy namespace, you must go to the profile menu and click on the tenancy. And on the tenancy details page under the tenancy information tab, you must copy the object storage namespace value. In my case, it is this one. And this is what I am using in my command where I've specified the tenancy namespace and slash separated by my user account ID. Now to get the auth token for this user account, you must click on the profile menu and go to my profile. Scroll down to resources section and here click on auth tokens. And you can click on generate token to generate an auth token for this account. Give it a suitable description and click on generate token. And you must copy this token and save it so that you can use it later on when you create the Docker registry secret. I'll hit the close button and I'll use the token that I just created. I'll replace the existing one with the one that I just created. Also make a note that it is recommended to surround special characters using single quotes. Now I'll copy this command and run it in my Cloud Shell terminal. I'll clear the screen first and let's paste the command here. I'll hit enter here and it says the secret OCIR secret has been created. Just to check the secret has been created or not, I'll use the command kubectl get secrets. As you can see, we have one secret in our cluster which is named as OCIR secret. Now let's go back to our manifest file and add the information about the Docker registry secret. In my front-end deployment manifest, under my spec section, I'll add an entry for image pull secrets. And I'll add the image pull secret property in the spec section for the containers towards the end. And in line with my container property, I'll use the image pull secrets property. And let me readjust the indentation here. Alright, now I have set up the image pull secrets and defined the name for my secret, which is OCIR secret, the one that we recently created in our Cloud Shell terminal. I'll save this deployment manifest file. I'll clear the screen here. And we all know that the front-end deployment that we ran earlier has errored out. Let's check the status of our deployment. It says deployment front-end is not ready yet. Let me first delete it. Well, the deployment front-end has been deleted. I'll reconfirm the same using kubectl get deployments command. And the entry for front-end no longer exists. Let me clear the screen. And now I'll create the front-end deployment again using the updated manifest file, which has the image pull secrets. I'll use the kubectl command and provide the file name. I'll hit enter. And it says the deployment front-end has been created. Let's reconfirm that using the kubectl get pods command. And if you notice, this time around we have the pods up and running as the deployment was able to pull the image from OCIR repository. Let's check the event description using kubectl describe pod command. Let's use one of the pod names. And I'll paste the pod name here. I'll hit enter. And let's check the event when the pod was getting created. The event says that the pod was assigned to node that ends with IP 150, and it is pulling the image from OCIR repository, and it was successful in pulling the image from this repository in 137 milliseconds and was able to successfully create container PHP Redis and started the container for us. Now that we have the containers for our front-end application up and running, we should be able to access our application using the same IP address that we used earlier. Because we did not change anything in regards to the front-end service or the Redis deployment and services, we just changed the front-end deployment to pull the front-end application image from OCIR repository. I'll use the kubectl get service command to see the load balancer's IP address. And this is the IP address of the load balancer. It hasn't changed. And if I navigate to the tab over here and if I hit refresh, I'm able to access my guestbook application. And you can notice we are able to fetch the messages that we stored in the Redis storage using the previous deployment. Since we did not change anything in the Redis storage deployment for our Redis leader or Redis follower pods, or Redis service for that matter. On this note, let me quickly add a message and just confirm if we are able to communicate with Redis storage. I'll hit submit. Well, this works and we can confirm that our new front-end deployment is still able to access the Redis storage pods. With this, we come to the end of this demo where we saw how to pull images from Oracle Cloud Infrastructure Registry repository during deployment on Container Engine for Kubernetes. I hope you found this video useful. See you in the next one. Thank you so much for watching. Hello and welcome to this lesson on supported labels for different use case within Container Engine for Kubernetes, also known as OKE. I am Mahendra Mehra, your senior OCI instructor at Oracle University. So let's get started. Container Engine for Kubernetes relies on several essential labels for creating and managing clusters. Among them are topology.kubernetes.io/zone, oci.oraclecloud.com/fault domain, and node.kubernetes.io/exclude from external load balancers. These labels play a pivotal role in orchestrating containerized applications within the Kubernetes environment. Before delving into the supported labels, let's revisit some fundamental concepts in OCI architecture. We will cover regions, availability domains, and fault domains. Let's talk about regions. A region is simply a physical location in the world where OCI hosts data centers. Regions are independent and can be located across countries or continents. In a nutshell, a region is a localized geographic area. Within a region, OCI hosts one or more physical data centers and calls this an availability domain. Every region can have up to 3 availability domains. This visual representation provides insights into the diverse deployment models supported by OCI across the globe. Talking about availability domains are data centers within a region that are connected to each other by low latency and high bandwidth network. Availability domains within a region don't share the same infrastructure such as power and cooling. Therefore, it's unlikely that an issue in one of the availability domains will impact other availability domains in the same region. Talking about fault domains Fault domains are separate hardware and infrastructure within the same availability domain, and each availability domain can have three fault domains. When creating your resources in OCI in an availability domain, you should choose to make them in different fault domains so they don't share the same infrastructure within the availability domains. Such a setup is ideal for better protection against hardware failure and maintenance downtime planning. Now let's delve into a closer examination of each label, starting with topology.kubernetes.io/zone. In Kubernetes environment, topology.kubernetes.io/zone is a crucial label automatically added by Container Engine for Kubernetes to each worker nodes within a cluster. We can utilize this label along with oci.oraclecloud.com/fault domain label to control the placement of pods on worker nodes in clusters spanning multiple availability domains. You should include the topology.kubernetes.io/zone label in the pod specification to specify the desired availability domain. Specify the availability domain and region for provisioning persistent volume claims when using the Flex Volume plugin. This ensures proper alignment with your storage requirements. When assigning a value to the topology.kubernetes.io/zone label, it is essential to use the correct shortened version of the availability domain in the Oracle Cloud Infrastructure regions. Most commonly, these shortened versions follow the format region identifier hyphen the availability domain number. For instance, UK London -1 -AD1, UK London -1 -AD2, and for Phoenix region it is PHX-AD1, PHX-AD2. Similarly for Ashburn it's US Ashburn AD1 and US Ashburn AD2. Now let's understand label oci.oraclecloud.com/fault domain. The oci.oraclecloud.com/fault domain label is automatically assigned to worker nodes, both managed and virtual, based on their fault domain placement within a cluster. This ensures that each node is accurately labeled according to its fault domain. Leverage this label in pod specifications to have precise control over where pods run within the cluster. By using this label, you can dictate the distribution of pods across fault domains, optimizing workload distribution. In regions with a single availability domain, employing the oci.oraclecloud.com/fault domain label becomes crucial for achieving high availability. This label helps distribute workloads and applications strategically across fault domains, mitigating the impact of potential hardware or infrastructure failures. For comprehensive control, include both topology.kubernetes.io/zone label and oci.oraclecloud.com/fault domain label in a pod specification. This allows you to specify both the availability domain and the fault domain of the worker nodes on which the pod should run. This ensures precise placement within the cluster. Now let's walk through a practical example to solidify our understanding. Consider a deployment having definition for Nginx pod that is configured to be created only if the cluster has worker nodes in fault domain 3 and in the given availability domain, that is PHX-AD1 in our case. If the cluster won't consist of worker nodes in PHX-AD1 availability domain and fault domain 3 within the availability domain, the pod is not created and remains in pending status. To bring this example to life, let's transition to OCI console and witness this scenario in action. This hands-on demonstration will provide a real-time visualization of how the labels we just covered influences pod creation within the cluster. I hope you're liking the video so far. See you in the next one. Thank you for watching. Welcome back. Let's resume from where we left off in our last video. Now I'll transition to my OCI console. For this demonstration, I'll be using an existing cluster. I'll click on the Kubernetes cluster service from the recently visited section. And for this demonstration, I'll be using the cluster labeled OCI OKE public labels demo. I'll click on this cluster. Let's check the node pool information for this cluster. I'll click on the node pools from the resources section. And this cluster consists of one node pool, that is pool 1. And the node pool 1 has 3 worker nodes in it. And from the placement configurations for the node pool, we can see that the availability domain 1, availability domain 2, and availability domain 3, that is all 3 availability domains within the Phoenix region has been configured, which means our worker nodes are distributed across 3 availability domains, that is for sure. But we also need to know which fault domains they are running within these availability domains. I'll restore the Cloud Shell terminal here. Clear the screen. I already have configured the kubeconfig file for this cluster and have the kubectl access to this cluster. I'll run the kubectl get nodes command. And we can quickly cross-check the node IPs. The node IPs are ending with .124, 217, and 75. I'll minimize this and let's check the IPs. Yes, it's 124, 75, and 217, which means I'm connected to the cluster that I'm talking about. As I pointed out earlier, label is automatically assigned to worker nodes, managed and virtual, based on their fault domain placement within a cluster. Let me quickly describe the nodes and check the labels assigned to these 3 worker nodes. Okay, let me get the node list of the worker nodes running in my Kubernetes cluster. I'll use the kubectl get nodes command. And now I'll describe each of these nodes to see the labels that have been set within these worker nodes. I'll use the command kubectl describe nodes and the node name, which is basically the IP address here. I'll hit enter. Alright, from the output, we must go to the labels section, and within the label section, as you can notice, we have these many labels assigned to our worker nodes, of which topology.kubernetes.io/zone is what we covered in the lesson. This defines the availability domain that the worker node is running on. Now we need to check the fault domain in which this worker node is hosted. And to check that, the label is oci.oraclecloud.com/fault domain. And as we can notice, this worker node is assigned to fault domain 1 within our availability domain 3 in the PHX region. Let me describe the other 2 nodes. I'll now replace the node name with the IP address of our worker node 2, which ends with IP.217. Let's scroll up and look at the labels for this worker node. Well, from the labels, we can notice that this worker node is placed in the availability domain PHX82, and from the oci.oraclecloud.com/fault domain label, we can confirm that it is part of fault domain 3 within availability domain 2 in the PHX region. And now let's describe the last worker node, which ends with .75. I'll quickly change the IP here, which is .75, and hit enter. Let's scroll up and check the details for this worker node. Well, this worker node is placed in availability domain 1, And from oci.oraclecloud.com fault domain label, we can confirm that it is part of fault domain 2 within availability domain 1 in PHX region. Now, based on the information that we just retrieved using the kubectl describe nodes command, I have created a table. Let me bring up the table for you. Well, these are the node IPs of our worker node, and these are the region in which they are placed. Of course, I'm running this demo in PHX region, which is why the region is PHX. And from the labels section for each of these worker nodes, I was able to populate this information. I'll clear the screen here. I'll now navigate to my Kubernetes examples directory. I'll now create a deployment within my Kubernetes cluster, which will create 3 pods of Nginx container image. Let's take a look at the deployment manifest file. Well, this is the manifest file which says the kind is deployment and the deployment name is Mahindra-deployment. The replica set says 3 replicas for the pods running Nginx latest image and exposed on port 80. I'll close this file and use kubectl apply command to create this deployment. Well, the deployment is created. Let's check the pod status. I'll use the command kubectl get pods, and this time I'll pass the flag --output equals to wide. Let's hit enter. Well, as you can notice, all our 3 pods for the Mahindra-deployment are up and running. And if you observe closely, all these pods have been equally distributed across the 3 worker nodes within our cluster. Which means whenever you run a deployment with more than 1 pod, the Kubernetes scheduler ensures that these pods are evenly distributed across all the worker nodes that are associated to the Kubernetes cluster. In our case, we had defined 3 replicas for the pods, and each of them are hosted on different worker nodes. Before we proceed with labels demonstration, it was crucial to highlight this fundamental aspect of Kubernetes. That is, when creating a deployment in a Kubernetes cluster, the cluster scheduler plays a pivotal role in ensuring optimal resource utilization. It achieves this by distributing pods evenly across all available worker nodes. Keep this in mind as we continue with our demo. Now let's move forward. In the next step, we'll leverage the powerful node selector property in Kubernetes to fine-tune our deployment. Specifically, we want to direct our pods to run on worker nodes hosted in fault domain 3 within OCI environment. And this level of control is achieved by utilizing labels. Let's first delete the existing deployment. I'll use the kubectl delete command, specify deployment, and the deployment name, which is Mahindra-deployment. Well, the deployment is deleted. Let's cross-check using the kubectl get pods command. There you go. All the pods are deleted. Now let me open up the deployment manifest. And towards the end, let's add a node selector property. And specify the label oci.oraclecloud.com/fault domain colon. In our case, it's fault domain 3. Let me provide the name. Now I have modified the deployment manifest to include node selector for the Kubernetes scheduler to take into account that it must deploy the pods in worker nodes that are placed in fault domain 3. In our case, there's only one worker node that's placed in fault domain 3, which is 10.0.10.217. I'll save this file and exit. Now let's create the deployment with the help of this new manifest file. I'll clear the screen first. I'll run the kubectl apply command to create the deployment. Let's hit enter. It says deployment created. Now let's check whether the pods are created and ensure that the pods are created on the worker node which is placed in fault domain 3. I'll use the command kubectl get pods --output equals to void. Well, from the output we can confirm that all our 3 pods are up and running, and as you can see under the node column, all the 3 pods are now running on the same worker node which is ending with IP.217, and like I showed you, the worker node running IP 10.0.10.217 is running within the fault domain FD3. I'll now delete this deployment and let's revisit our example. Now, based on the use case defined in our example, we don't just want to restrict the pod creation on a fault domain, but also in a particular availability domain. In this use case, it is phx81 and fault domain 3. Let's head back to the OCI console and add this label within the node selector to select the availability domain 1 in phx region. I'll open up the deployment manifest file again. And now I'll add an entry for the availability domain label. Now, based on the new information that we have provided in the node selector property, the pods will only run on the worker nodes that have been deployed in fault domain 3 within phx81 availability domain. Let me save this file. But from the information that we have, there is no such worker node that is running on fault domain 3 within availability domain 1. The only worker node that's running on availability domain 1 is 10.0.10.75, but the fault domain that it is running in within AD1 is fault domain 2, which means we don't have an available worker node that meets the requirement in the deployment manifest. In this case, let's see what would happen. Let me create the deployment using kubectl apply command. Well, now let's check the pod status. Well, from the output, it's clear that the pods are in pending status as the kube scheduler is unable to locate any worker node that's running on fault domain 3 within availability domain 1. And now if I go to the deployment manifest file and change the requirement for the fault domain to fault domain 2 instead of fault domain 3, the pods will be scheduled on worker node with the IP 10.0.10.75. I'll first delete the deployment using kubectl command. I'll now open up the deployment manifest and let's quickly edit the requirement here, which is I'll change the fault domain here from 3 to 2 as we have a worker node running in fault domain 2 within phx81 availability domain. You save the file and now let's run the deployment again. Alright, the deployment is created. Let's check the pod status. Well, from the output, it's clear that the pods are now in running status and they all have been deployed on node with the IP address 10.0.10.75, as this is the only worker node that's running on fault domain 2 within availability domain 1 in phx region. I'll clear the screen. I hope you're liking the video so far. See you in the next one. Thank you for watching. Welcome back. Let's resume from where we left off in our last video. Now let's dive into the intricacies of node.kubernetes.io/exclude from external load balancers label. OKE introduces the service node exclusion feature gate, and supporting this label, it allows you to selectively exclude specific managed nodes from OCI load balancer backend sets. By strategically excluding certain worker nodes, you gain the ability to enhance the load balancer update speed. This is particularly beneficial as it reduces the number of nodes that needs to be managed, ultimately optimizing the efficiency of load balancers operation. However, it is important to note that this label is not supported with virtual nodes. To practically implement exclusion, follow these steps. To exclude a worker node, assign the label using the command kubectl label nodes and the node name, and then use the label node.kubernetes.io/exclude from external load balancers and set its value to true. Once applied, the worker node remains excluded from the load balancer's backend servers irrespective of the label's value. Even if you specify the label and set it to false, the node remains excluded. To remove the exclusion label from a node, you must use the following command. Run the command kubectl label nodes and the node name and specify the label node.kubernetes.io/exclude from external load balancers and add a minus sign at the end. Upon running this command, the exclusion label from the worker node will be removed. For bulk exclusion, you can add the label to the node pool's Kubernetes label property during the node pool creation or modification. Well, let's see this label in action. Let's go to the OCI console. Now, first thing that I'll do is I'll run a clean deployment by removing the node selector property. I'll now open up the deployment manifest file and remove the node selector property from the specification. I'll save this file and I'll run the deployment again using the kubectl apply command. Well, let's check the pod status. Alright, all our pods are up and running and they all have been hosted in different worker nodes. Now I will create a service of type load balancer to expose the pods running in this cluster. I'll open up the service manifest file. This is the manifest for our service, and as you can notice, the kind says service. This is the name of our service, which is Nginx load balancer service. Under the spec section, we have label selector that define the pods that should be exposed using this service. The type is set to load balancer, and under the port section, we have specified the name, that is HTTP. The port is 80. The target port that it should expose on container is 80, and the protocol to be used is TCP. I'll close this file now. I will now go ahead and create this service using the kubectl apply command. Now before I hit enter, let me quickly minimize the Cloud Shell terminal. Basically, I want to resize this terminal. Alright, this looks good. Let me clear the screen. And now let's go to our load balancer service. I'll click on load balancer here. At present, there is just one load balancer that is active. Now when I hit enter here, the Kubernetes controller will create another load balancer for us within our OCI region, and we will monitor the backend set for that particular load balancer. I'll hit enter now. It says the load balancer service created. Alright, we can see a new entry has been created here, and the state says that the load balancer is in creating state. Let's also run kubectl get service command. Well, there you go. Our service nginx load balancer service of type load balancer is created, and an external IP address has been assigned to it. And we can confirm that from the OCI console as well, as both this IP address in the console and in the terminal matches. Alright, now overall health for this load balancer is set to OK. Alright, now I will take a closer look at the load balancer we just created using the service of type load balancer. I'll click on this. If I scroll down, I'll select the backend sets. And as you can notice, the number of backend sets for this load balancer is 3, as there are 3 worker nodes in our cluster. I'll click on this entry over here. And let's click on the backends under the resources section. And there you go. These are the 3 worker nodes that are connected to our cluster and are also acting as backend sets to our load balancer that we just created. Now it's time to exclude a worker node from the backend set, and for which we'll be running the command kubectl label nodes and the node name, and specify the label, that is node.kubernetes.io/exclude from external load balancer, and set its value to true. Now let me go ahead and remove the first entry of worker node, that is 10.0.10.124 from the backend set. Let's exclude this worker node from the backend set, for which I'll run this command kubectl label nodes, and I've specified the node name, that is 10.0.10.124, and set the label to true. I'll go ahead and hit enter. Well, the node has been labeled, and you will observe in some time from now this entry will be deleted from the backend sets. Well, the entry for our worker node 10.0.10.124 has been erased from the backends, and now this backend set has only 2 backends. And like I said, and as we discussed, to remove the exclusion label from a node, we can use the same command, but this time just add a minus sign at the end of the command. I'll clear the screen first. Now I'll use the command kubectl label nodes and the node name that I just deleted, and provide the label node.kubernetes.io/exclude from external load balancers, and just append a minus sign towards the end and hit enter. Now once the node has been unlabeled, we will be able to see the entry again in the backends for our load balancer. Alright, as you can notice, the entry for the worker node is again listed in the backends. It's currently undergoing a health check, and once the health check is complete, it will be part of the load balancer backend set. Well, the health check for our worker node 10.0.10.124 is now complete, and it says OK, which means this worker node along with the other 2 is now part of the backends for our OCI load balancer. To wrap up, we've explored the critical role of labels in Kubernetes. These labels empower precise control, enhance availability, and optimize load balancing in your cluster. I hope you enjoyed the video. See you in the next lesson. Thank you for watching. Hello and welcome to this lesson on OCI service operator for Kubernetes. I am Mahendra Mehra, your senior OCI instructor at Oracle University. Let's get started. OCI service operator for Kubernetes is an open source Kubernetes add-on that transforms the way we manage and connect OCI resources within our Kubernetes clusters. This powerful operator enables you to effortlessly create, configure, and interact with OCI resources directly from your Kubernetes environment, eliminating the need for constant navigation between the Oracle Cloud Infrastructure Console, CLI, or other tools. With the OCI service operator, you can seamlessly leverage kubectl to call the operator framework APIs, providing a streamlined and efficient workflow. OCI Service Operator for Kubernetes is built using the open source Operator Framework Toolkit. The Operator Framework manages Kubernetes native applications called operators in an effective, automated, and scalable way. The Operator Framework comprises essential components like Operator SDK. This leverages the Kubernetes Controller Runtime Library, providing high-level APIs and abstractions for writing operational logic. Additionally, it offers tools for scaffolding and code generation. The other essential component is Operator Lifecycle Manager, also abbreviated as OLM. OLM extends Kubernetes by introducing a declarative approach to install, manage, and upgrade operators within a cluster. The OCI Service Operator for Kubernetes is intelligently packaged as an Operator Lifecycle Manager bundle, simplifying the installation process on Kubernetes clusters. This comprehensive bundle encapsulates all necessary objects and definitions, including CRDs, RBACs, config maps, and deployments, making it effortlessly deployable on a cluster. As we explore the capabilities of OCI Service Operator for Kubernetes, one of its standout features is its seamless integration with a range of OCI services. This integration empowers you to effortlessly provision and connect with the following OCI services. The first one is Autonomous Database, specifically tailored for transaction processing, mixed workloads, analytics, and data warehousing. Enjoy automated patching, upgrades, and tuning, allowing routine maintenance tasks to be performed without human intervention. The next on the list is MySQL HeatWave, a fully managed database service designed for developing and deploying secure cloud-native applications using widely adopted MySQL open source database. Third on the list is OCI Streaming Service. Experience a fully managed, scalable, and durable solution for ingesting and consuming high-volume data streams in real time. Next is Service Mesh. This service offers a set of capabilities to facilitate communication among microservices within a cloud-native application. The communication is centrally managed and secured, ensuring a smooth and secure interaction. The OCI Service Operator for Kubernetes serves as a versatile bridge, seamlessly connecting your Kubernetes clusters with these powerful Oracle Cloud Infrastructure services. In summary, integrating OCI Service Operator for Kubernetes into your clusters streamlines the management and interaction with OCI services. With automated provisioning and seamless Kubernetes native integration, you can effortlessly leverage powerful services like Autonomous Database, MySQL HeatWave, streaming, and Service Mesh within your Kubernetes deployments. I hope you found this lesson insightful. See you in the next one. Thank you for watching. Hello and welcome to this demo on adding OCI Service Operator for Kubernetes to OKE cluster. I am Mahendra Mehra, your senior OCI instructor with Oracle University. Let's get started. I'm already logged in to the OCI console and currently on the clusters details page of the cluster we'll be using for this demonstration. I'll click on the access cluster button and copy the command to set up the cluster access. I'll paste the command on a local machine that I am using for this demonstration. As you can notice, the kubeconfig has been written and we have the access to the cluster. I'll confirm the same using kubectl getNodes command. From the output, it is confirmed that we are connected to the cluster. The first step as part of this demo is to install the operator SDK. You can visit the sdk.operatorframework.io website for the installation step. There are multiple ways in which you can install operator SDK. I'll be going for install from the GitHub release method. First step is to set platform information. I'll copy the export command given on the screen and paste it on a local machine that I'm using. Next step is to download the operator SDK binary for the platform. I'll copy the command and paste it on the local machine. Well, from the output, we can confirm that the binary has been downloaded and the total size it consumed is 89.2 MB. The next step is to verify the downloaded binary, for which we will import the operator SDK release GPG key. I'll paste the command and hit enter. As you can notice, the public key has been imported. Now I'll download the checksum file and its signature and then verify the signature, for which I'll be running the commands as given on the instruction page. Once I run the command, we must see the following output. Well, the output matches with the one as given on the instructions page. Now we will make sure that the checksums match. I'll copy the grep command and the output of the grep command should return us the following on the screen: operator SDK Linux AMD 64 OK. I'll paste the command here. And as you can notice, it returns OK, which means the checksum has matched. Now the next step is to install the release binary in your environment path. I'll copy the command chmod and paste it on my local machine. I'll hit enter. Now once we have installed the operator SDK, the next step is to install Operator Lifecycle Manager, which is also known as OLM. To install OLM, we will use the following command, not specifying the version flag as we'll be going for the latest version. This will take some time. Well, OLM version latest has been installed successfully. Now let's verify the installation by running the operator SDK OLM status command. I'll copy the command. Well, the command must return us the following output. Alright, as you can notice, it says all the CRDs and other resources have been installed. The latest version that we are using is version 0.26.0. Now the next step is to deploy OCI service operator for Kubernetes, for which we'll enable the instance principles first. We will be creating a OCI dynamic group where the worker node instances or the compartment where the worker node instances are running. I'll click on the navigation menu and go to identity and security. Click on domains. I'll select the root compartment and click on default. Go to dynamic groups. Click on create dynamic group. Provide it a suitable name. I've given it a name OSOK-DYN-group. Since description is mandatory, I'm providing a description for it. Now I'll be providing the dynamic group rule, which defines the resources for this dynamic group, which is all the instance running in compartment CTD OKE. I'll click on create. Now I'll set the policy for this dynamic group. I'll click on policies and go to the parent compartment of my CTDO compartment. Click on create policy. Give this policy a suitable name. Let's provide this policy a suitable name and a description. I will now copy the policies as specified in the official documentation. And these policies allow our dynamic group to access or manage resources within tenancy, or you can also scope it to a compartment. With these policies, we are allowing our OCI service operator dynamic group, which we created earlier, to have the managed permissions for the MySQL family resource type and other permissions such as subnet read, subnet attach, subnet detach, VCN read, and compartment inspect within the tenancy. The next step is to enable user principal. The OCI service operator for Kubernetes needs OCI user credential details to provision and manage OCI services or resources in the customer tenancy. And this approach is recommended when OSOK is deployed outside OCI. We will also be creating Kubernetes secret in the later steps, but for now, the OSOK will be deployed in OCI service operator system namespace. And for enabling user principals, we will have to create the namespace before deployment. I'll copy the YAML file code and paste it on our local machine. Here I'll create a manifest named OCI service operator system.yaml and paste the manifest code I just copied for the namespace. I'll save this file and exit. Now let's apply this manifest using kubectl apply command. I'll hit enter. And the output says namespace OCI service operator system created. Now the next step is to create user secret. The secret should have the below keys and respective values for it. It includes the OSID of your tenancy, the fingerprint of your OCI user, OSID of the user, OCI user's private key using which the fingerprint was created, passphrase of the private key, and the region in which the OKE cluster is running. The value should be in OCI region format, as shown in the example US-hashban-1. I'll copy the command given on the screen to create a secret by the name OCI credentials. I'll copy it and paste it on a WordPad file and replace the placeholders with respective values. Let's break down the command. The command is kubectl-n OCI service operator system, which is the namespace where we are creating this secret. Secret is of type generic with the name OCI credentials. From literal tenancy specifies the tenancy OSID, and from literal user specify the user OSID. From literal fingerprint is where we specify the user's API fingerprint. From literal region is where we specify the user region. And from literal passphrase is left blank. And from private file is where we specify the path to the user's private key. I've already populated the required values as per my environment. I'll paste it on the local machine and create the credential. Well, the output says secret OCI credentials created. The next step is to deploy OSOK, which is the OCI service operator for Kubernetes. The OCI service operator for Kubernetes is packaged as OLM, Operator Lifecycle Manager bundle, for making it easy to install in a Kubernetes cluster. And we can download the bundle as a Docker image. I'll copy the Docker pull command as given on the instructions page, paste it on the local machine. The version that I'll be using is 1.1.9, which is the latest version for the OCI service operator bundle. Well, it has successfully pulled the operator image. This OLM bundle contains all the required details like the CRDs, RBACs, config maps, deployments, which will install the OSOK in the Kubernetes cluster. Now to install the OSOK operator in the cluster, I'll copy the command operator SDK run bundle and provide the image path. I'll paste it on the local machine and hit enter. Well, the output says OLM has successfully installed our OCI service operator version 1.1.9-2. When not required, you can undeploy the OSOK, and that can be easily done using the OLM by running the command operator SDK cleanup OCI service operator. With this, we come to the end of this demo where we saw how to add OCI service operator for Kubernetes to our OKE cluster. In the next part, we will see how to use the deployed OSOK on your Kubernetes cluster to deploy the Oracle MySQL database service. I hope you found this demo useful. See you in the next one. Thank you for watching. Hello and welcome to this demo on Deploy Oracle MySQL DB System Service from Container Engine for Kubernetes Cluster. I am Mahendra Mehra, your Senior OCI Instructor with Oracle University. In this lab, we will use the deployed OSOK, also known as Oracle Service Operator for Kubernetes, that we installed in the previous demo to deploy the Oracle MySQL database service. Oracle MySQL database service is a fully managed database service that lets developers quickly develop and deploy secure cloud-native applications using the world's most popular open source database. Oracle MySQL database service is also offered via OCI service operator for Kubernetes, making it easy for applications to provision and integrate seamlessly with MySQL databases. Let's get started. I've already logged into the OCI console, and this is my OCI dashboard. Firstly, I'll go to the dynamic groups that we have created for this demonstration. We had already done it in the previous demo. It is the instance principal dynamic group that we created for all the worker node compute instance within our compartment CTD-OKE. As you can see from the rule that we had written, it's for all instances within our CTD-OKE compartment. Now this dynamic group will require some policies to deploy the Oracle MySQL database service. We already have the policies in place. I'll take you to the policies page and click on the OSOK dynamic group policy. And these are the set of 3 policies we need to deploy MySQL database service. And this is the third policy which I added later on to use tag namespaces in tenancy. Now I'll take you to the MySQL DB service by clicking on databases from the hamburger menu, and then I'll click on the DB system under MySQL Heatwave. I'll select my CTD-OKE compartment. And as you can observe, there are no DB systems currently available in my CTD-OKE compartment. Now I'll move to my local machine, and here I'll switch to the directory where I have all these service manifests created to run this demo. Let me cd into service operator directory. Let me do an ls. Provisioning of MySQL DB system requires the user to input the admin username and admin password as a Kubernetes secret. OSOK acquires the admin username and password from the Kubernetes secret whose name is provided in the specification file. Let me open up the specification file, which is mysql_secret.yaml. Well, this is the manifest for our Kubernetes secret, where the API version is set to v1 and the kind is set to secret. The metadata section contains information about the name of the secret. Let's change the name of the secret here. I'll change it to OSOK MySQL. Now the type of this secret is set to opaque, And under the data field, we must specify the username and password for our secret. Make a note, the username and password value we provide in this file should be in the base64 encoded format. Now I'll close this file and use the echo command followed by the string, my username, and I'll pipe it to base64 command, which will generate the base64 encoded string for my username Mahendra. I'll copy the string and save it in a notepad file. Now I'll generate a base64 encoded string for my password. And I'll copy this base64 encoded string and save it in the notepad file. Now let's go back to the manifest file and update the username and password value with the base64 encoded strings we generated. I'll paste the value for username, and now I'll paste the value for password, which, let me remind you, is in base64 encoded format. Once done, I'll now save this file. Now I'll use the kubectl apply command to create this Kubernetes secret. I'll hit enter, and there you go, the secret OSOK MySQL has been created. The MySQL DB system now can be accessed from the secret, which will be persisted as part of the provision bind operation of the custom resource. Now the next step is to set up a manifest file that allows our OSOK MySQL DB system controller to automatically provision a MySQL DB system based on the inputs we provided in the manifest file. I'll open up the manifest file, which is mysqldbsystem.yaml. Let's now break down the manifest file. The API version specifies the version of API being used, which is oci.oracle.com/v1beta1. The kind specifies the kind of resource being created, which is MySQL DB system. Metadata contains metadata about the resource, where we specify the name of the custom resource object under the name field. The specs section defines the state of the resource, where compartment ID specifies the OCID of the compartment where the resource will be created. In our case, it is CTD OKE compartment, so I'll replace it with the OCID of my CTD OKE compartment. The display name is the name of the MySQL DB system that we are creating. The shape name specifies the shape of the MySQL DB system. Let me take you to the MySQL DB service page and talk more about the shape and configuration information. On the MySQL DB page, I'll click on the configurations link and I'll scroll down to the shape that I'm using in my manifest file. It is MySQL VM standard E3 1.8 GB. I'll click on the shape, and this opens up the configuration detail of the shape that I've chosen. Now the next step is to provide the subnet ID. This specifies the OCID of the subnet where the MySQL DB system will be provisioned. I will replace it with the subnet ID of my worker node subnet. Now let's go and check the OCID of our worker node subnet. I'll go to the cluster service page. Let me choose my CTD OKE compartment and click on the cluster that we are using for this demonstration. I'll go to the node pool section and click on the pool name. Now from the pool details page, I'll click on the worker node subnet link. And from the subnet information page, I'll copy the OCID of our worker node subnet, which is available under the OCID field. I'll click on the copy link and go back to our manifest file and paste the OCID here. Now the configuration section specifies the configuration of MySQL DB system, including an ID which represents the configuration should be replaced with the actual OCID. Now I'll go to the configurations page and copy the OCID from the configuration information of the shape that I've chosen for the MySQL DB system. which is MySQL VM standard E3 1.8 GB. I'll copy the OCID and paste it under the ID field. Now the availability domain specifies the availability domain for the MySQL DB system. I will replace it with the availability domain that our worker nodes are running in. I'll go back to the node pool information page and copy the availability domain detail and paste it in the manifest file under the availability domain field. Now under the admin username field, I will specify the admin username. Here the secret indicates that the admin username is stored in a secret. So I'll specify the name of the secret containing the admin username, which is OSOK MySQL. And similarly for admin password, we have the password stored in a secret, that is the Kubernetes secret with the name OSOK MySQL. Description is to provide a description for the MySQL DB system. And the data storage size in GBs specifies the data storage in gigabytes, which is 15 RKs. Port specifies the port for MySQL DB system, and port X specifies an additional port for the MySQL DB system. I'll save this file and close. And now I'll use the kubectl apply command to apply this manifest on our Kubernetes cluster. Well, the output confirms that MySQL DB system sample has been created. I'll confirm the same using the kubectl get MySQL DB system -o white command and check the status of our MySQL DB system. Well, we have the entry, but the status is not present as of yet. I'll go to the MySQL DB system service page on the OCI console, and we will monitor the progress on the OCI console. Well, as you can observe, the sample DB MySQL DB system is getting created as the DB system state says creating. This will take some time before the sample DB gets created. After a while, the DB system state is now set to active, which means our sample DB MySQL DB is active and available. I'll go back to the shell and run the kubectl get MySQL DB system -o white command. And as you can observe, the status is now active and we have received an OCID for our sample DB. If I cross-check the OCID, the last 4 letters are U5OQ. Let's go back to the OCI console and confirm the same. Yes, they both are same. Now I'll run the command kubectl describe MySQL DB system and provide the name of our custom resource, which is MySQL DB system -sample. As you can observe from the output, we get to see the details of our custom resource, including its metadata information. Under the spec, we can notice the admin password and username are being fetched from a secret file, the availability domain where the DB system is deployed, the compartment's OCID. Under the status, we can check that the type is set to active, and the OCID of our MySQL DB, that is sample DB. And from the event section, we can notice the logs of the creation process. We can also bind to an existing MySQL DB system. In this case, only the ID is required within the custom resource specification file. I've created a manifest for the same, and as you can notice, the kind is set to MySQL DB system. Under the metadata section, we specify the name of our custom resource, and under the spec section, there's only one field that we need to populate, which is the ID. ID here is the ID of our existing DB system. You can also update a number of parameters of the MySQL DB system. All you need to do is specify the parameters within a specification file. For example, if I open up a sample file, here all you need to do is set the kind to MySQL DB system, and under the spec section, simply change the ID, display name, description, within the configuration section, provide the ID of the new configuration, and under the freeform tags section, you can change the freeform tags as well as defined tags. Once you have these values updated, simply run the kubectl apply command and update your existing MySQL DB system. With this, we come to the end of this demo where we saw how to use the Oracle service operator for Kubernetes on an OKE cluster to deploy the Oracle MySQL database service. I hope you found this demo interesting. See you in the next one. Thank you for watching. Hello and welcome to this lesson on defining Kubernetes services of type load balancer. I am Mahendra Mehra, your senior OCI instructor with Oracle University. So let's get started. When defining a Kubernetes service of type load balancer to expose applications to the internet or local network, OKE, which is Container Engine for Kubernetes, provides flexibility in how this service is implemented. There are two key options: utilizing an OCI load balancer configured in the Oracle Cloud Infrastructure Load Balancer service. And the other one is employing an Oracle Cloud Infrastructure Network Load Balancer configured in the OCI Network Load Balancer service. Let's now delve into the nuanced differences between these two implementations. Let's explore the disparities between an OCI load balancer and an OCI network balancer. OCI load balancer operates at OCI layer 4 TCP and layer 7 HTTP as a proxy. It provides customization options for minimum and maximum bandwidth ranging from 10 Mbps to 8000 Mbps. On the other hand, OCI network load balancer serves as a non-proxy load balancing solution that conducts pass-through load balancing for OCI layer 3 and layer 4 workloads. Here you get to experience the benefits of an elastically scalable regional virtual IP, also known as VIP address, adapting to client traffic with no minimum or maximum bandwidth configuration requirements, along with benefits of flow high availability, source and destination IP preservation, and port preservation. Understanding these distinctions enables you to make informed choices based on your specific network requirements. When provisioning an OCI load balancer for a Kubernetes service of type load balancer, you gain the ability to load balance transport layer 4 and layer 7 traffic, especially TCP and HTTP. You also get to perform SSL/TLS termination directly at the load balancer. It's important to note that during this provisioning process, Container Engine for Kubernetes takes care of automatically creating security rules. These rules facilitate inbound and outbound traffic to and from the load balancer's subnet, ensuring a seamless and secure networking environment for your Kubernetes services. To provision an OCI load balancer for a Kubernetes service of type load balancer, it's crucial to define a service with the appropriate annotations. Specifically include the following annotation, that is oci.oraclecloud.com/load balancer type, and pass the value as LB. It's worth noting that LB is the default value for the OCI.oraclecloud.com load balancer type annotation. If you omit this annotation in your service definition, the default value will be used. Let's now navigate to OCI console and observe the practical implementation of these steps. I've already logged into my OCI account and currently I'm on the Kubernetes clusters page. I'm already connected to the first Kubernetes cluster in the list, which is OKE public demo 1, where I'll be performing this demonstration. I've already launched my Cloud Shell machine. Let me restore it. I've already created a manifest for this demonstration. Let me open up the manifest in the code editor. Maximize the window. There are two parts to this configuration file. The first part defines deployment of our Nginx, requesting it to be hosted on 3 pods and running the Nginx latest image. Also accept traffic to the containers on port 80. As we move down, the second part of this configuration file defines a Nginx service. As you can see, the kind specifies service, which uses the type load balancer to balance the Nginx traffic on port 80. Now, to create the deployment and service defined in this nginx-lb.yaml manifest file, I'm already connected to a Kubernetes cluster as I mentioned earlier. I'll minimize the code editor window and let's apply this manifest to our Kubernetes cluster. I'll be running the command kubectl apply -f and the name of my manifest, which is nginx-lb.yaml, which I just explained you. I'll hit enter. It says deployment my nginx created as well as the service my nginx svc created. Well, as we have created the Kubernetes service of type load balancer, the OCI load balancer will be created. I'll minimize the Cloud Shell window and let's navigate to our load balancer service. I'll click on load balancer. Well, there you go. The load balancer is already created and active, and the IP assigned is 152.70.154.147. I'll restore the Cloud Shell terminal. And now let's check whether the deployment and services are created. We'll run the command kubectl get all. Well, as you notice, 3 pods of my deployment my-nginx are created and they are all in running state. Also, the service my-nginx svc of type load balancer is created and has been assigned an external IP, which we just confirmed from our load balancer page. I'll copy this IP and paste it on a new tab. There you go. We are connected to one of the pods which is hosting our Nginx website. Let's transition back to our slide. We've covered a lot in this video. To avoid overwhelming you, let's hit a pause here. Take your time to absorb this information and I'll see you in the next video. Thank you for watching.